Hello and welcome to the first tutorial on pyiron. Here I visit the pyiron website, so that's pyiron.org. You can learn more about the team, the collaborators, applications using pyiron, read the documentation, or the getting started guide, and the news about pyiron. Finally, you can browse our code on GitHub and install pyiron using the conda package manager, so that's conda install -c conda forge pyiron. Below you see the screenshot that we already discussed in the previous presentation and the code examples we also discussed. Now, more to the bottom of the page, you find the latest news about pyiron. This can be announcements of workshops or releases of new pyiron versions. And then finally, you can try pyiron using mybinder, and that's what we're going to do in this tutorial. So I click on this link, it opens a new tab. And mybinder is a public cloud solution which basically uses Docker containers to run Jupyter environments directly in your browser. So for pyiron, this allows you to try pyiron in your browser without the need to install anything and testing it directly in your browser. And you see here the Jupyter environment is loaded. I already increased the zoom to make it more readable for you. So I assume for you it's going to be a bit more smaller, but you can then increase this font size. Good. You find already there are quite a couple of examples available inside the pyiron environment. I highly recommend starting with the first steps example. You can also take a look at the other ones, depending on your interest. For this tutorial, we will start with a blank new notebook to get to know the notebook environment and also how to use pyiron in this notebook. We clicked on the launcher to open the new notebook, and now we can rename this notebook to give it a name. So here in demonstration. And then we can start our first session by from pyiron import project. So we want to import the project object, and then I can execute the cell by pressing Shift and return. And then I can create an object from this. So I create an object instance, I create a new demo, and that you already see here. So I created now a folder named demo, so that projects in pyiron are always associated with folders in the file system. You can also see the path of the project where we find the project. Before going deeper into the pyiron part, let me briefly motivate the use of Jupyter notebooks rather than the classical terminal. For this, I now press Escape and A to create a new cell. And let me shift from code mode to markdown mode. The advantage here is really that we can add documentation directly within our environment. And so here I use now the markdown language to add some documentation, and for here we just write down the keyboard shortcuts. Keyboard shortcuts used in this tutorial. You could maybe write down more information about your project here. So the first one is tab. That's basically just auto-completion. And then we have tab plus shift. And that's for documentation. We have shift plus enter. And we also want to have this code. So use the markdown notation here to execute cells. Not just a single cell. And we have escape plus A for a new cell above, and escape plus B for a new cell below. So there are more keyboard shortcuts for Jupyter, obviously. These are the primary ones and the ones we definitely use in this tutorial. Good. With this, we can jump right into it. Let's say we created our first project. And before looking at the individual features of the project object, we will just use it to create new objects. So in this case, we want to start with atomistic structure. So we can have our structure object here. We again make a headline, and then we create our structure, and then we use a project object to create a structure. And then we can already use tab here to see what are the different options. And then there's already one, so that's ASE bulk. So we use ASE. ASE is the atomic simulation environment, and then we can use the bulk function to create a bulk structure. So we can now use shift and tab to get the different parameters. We want to say the name of the structure. It should be an aluminium structure. And the other parameters are optional, so we could define the crystal structure, the A letters, the C letters, the C over A ratio, and also define autorhombic cluster structure. But in this case here we only want to make it a cubic structure. We can now look at our structure object directly, just executing it again, and we see, okay, there are 4 atoms, we have periodic boundaries, we have the lattice constant. The lattice constant now is based on the parameter database inside ASE, but as we saw before, we could now change it and increase the lattice constant, and then we would have this lattice constant here. As you already noticed, while executing these cells, they are numbered. Right? So we see the number of execution, the order. And this is important as we see here. So now we notice we executed these cells twice. We no longer have access to the previous version without the A parameter. And so they are numbered, but that's one of the risks of using Jupyter Notebook, to get confused with the order how you executed your simulation cells. To prevent this, we can always, when we're finished with our notebook, try to execute it again from top to bottom, so using the kernel and then kernel restart run all cells. This will again execute all cells of the Jupyter Notebook, and we can see that now the order is correct. Right, so before we hand over a notebook to the next person for them to reproduce our results or to continue working on a topic, we should always make sure that the notebook executes from top to bottom. Good. In addition to the text-based representation, we can also now plot the structure directly in the browser. You use the plot 3D function, and you can see, okay, it's our cubic structure as we would expect. We can also use default Python commands, so we can get the length of the structure by using the length command. We can delete an atom from the structure by using the del command, so here delete the atom number 0. And we can also replace, and we can look at the structure just to confirm that it was deleted, and then we can replace an atom inside the structure, also following the same idea. So now I replaced the first atom, an aluminium atom, with a nickel atom, and you can see it's also replaced in our text-based input. Finally, we can repeat our structure. So for this, I create a new variable, structure repeat, and I assign my structure and call the repeat function. The repeat function can either take a single integer, or we can have a list of up to 3 integers. So we have 1, 2, 3, 4. So I do 2 repetitions in x direction, 3 repetitions in y direction, and 4 repetitions in z direction. And you can then visualize your structure directly in here. Alright, so we can already see how we build a more complex, larger structure. In our browser, we can rotate it, we can look at it, we can center it again, we can even look at it in a full screen view. So that's more helpful to analyze the structure and get a feeling, even before we start our very first calculation. Good. So now that we have our repeated structure, let me move on and talk a bit more about features that go beyond the classical structure class in ASE. So the pyiron atoms are based on the atomistic structure model, atomistic simulation environment, so the ASE structure, but we extend it by adding functions like the plot 3D, or also the neighbor environment. I want next to talk about the neighbor environment. So then I make a new headline for the document to be structured, and then I can create, or maybe I create a new structure. I can use the ESE part, and you already see that I used the auto-completion quite a lot. So I have an aluminium structure again, and I want it to be cubic. In addition to the repeat function, we also have the set repeat function, which basically applies the repetition to the very same structure. So we can confirm this here by looking at the length of our structure, and we see we have 108 atoms. We can now calculate the neighbors, again from our structure object. So that's really one of the key features, and that all the objects are connected in pyiron, which helps us then to build the connection or the relation between the different objects. So we set, let's say, 50 neighbors here. And then if we now look at this neighbors object and look at the distances, for example, and the shape, you see that we have 108 atoms. So we have 108 in the first dimension, and then 50 neighbors per atom, so 50 in the second dimension. To now visualize this, we import the matplotlib library. Import the pyplot SPLT, and then we can plot the histogram of the distances. And we want to flatten those because we don't want them per atom, just one big array. And let's say we want to make 50 bins. In addition, we should add labels to be able to understand our data. So here we want this is the distance, and as a histogram, we should also add the counts. And this is 1. Right, and we can see the different neighbor shells and how they are connected. Good. So now we want to go one step further, and that's creating structures with like an external code. And in this example, I just want to demonstrate an SQS code and how it can be interfaced in pyiron. For this, we create our first job using the create job function. The create job function takes basically just 2 inputs. That's the job type, which we can get from our project object. We can get here the SQS job, and then the job name. We name our job just SQS. We can then assign a structure object to this job. It's our reference lattice. So we take our lattice structure, and we can look at the input of our SQS job. And so we still have to define the mole fraction. So maybe that's what we do next. So we say we want aluminium, 50%, and then also nickel, 50%. And in addition, we should decrease the number of iterations in the input. Iterations to, let's say, 1,000. I do this here because my binary environment is limited and I want to get results quickly. If you have a cluster or a computing cluster, you could also list the queues directly from your object, or increase the number of cores. But both is not necessary here on my binder because we don't have any access to high computing resources here. So we will just execute this job. And we can then look at the result, and we get a list of structures. This is our structures. We get this here, and we can then select the first structure. I select structure as class. And plot our SQS structure. And you can nicely see your random structure, which would then be used to calculate this relation and the stability of the space at this given concentration. Good. Now maybe let me briefly also talk about the job management in pyiron. So we'll just be doing the job table. And we see here the job ID, so it's just an integer ID, then we see the job status is finished, the chemical formula, the name of the jobs, the parse when it was started and stopped, and so on. In addition, you see that as we were executing the job, it created an HDF5 file, and this HDF5 file contains basically all the data of this calculation. With the job name, it's now possible to reload this job. And we do this again using the project object. And we here just give the job name. And we can then look at the reload input, look at the input of our object, and see the mole fraction, and so on. So we can now say, okay, we want to change this input. We want to change the mole fractions. Let's say we updated our opinion and we want to make our meaning with 75% and nickel only. String and nickel only is 25%. And now if we want to execute this again, we run, and then we add an additional flag that's delete existing. If we don't do this, pyiron will just reload the job, right? So we can do this, execute the job again. It says, okay, the old job was deleted, and we can then again look at our structures, and the first one, and plot this in 3D. To validate, okay, we're now at this new concentration, right? So there are more nickel atoms and more aluminum atoms and less nickel atoms. Another option would be to take this structure object and just get the chemical formula. So we do this here. 25. This is the one inside this object, and then we can use this and again use the auto completion. Get chemical formula. Right, so we can see the ratio that we have for this specific structure. Good. So this being said, maybe one last point. If you now have your work done and you think about publishing it, you can always use pyiron also to list your publications, and this would list all the different papers. So here it lists the pyiron paper, and then the ASE paper, and finally the SQS paper. So you'll get a list of publications of the different modules that you used in your specific demonstration. So to summarize this, maybe let me go back and briefly scroll over this notebook. We started with the basics of Jupyter notebooks. Now we create our first project object. We then use the project to create other objects and also look at the job management. The first object that we created was the structure object, so it's shown here with the bulk. We then looked at the properties of the structure object and how we can handle it. It behaves like other Python objects with the lang function and the delete function. How we can set other elements, and how we can repeat the structure. Look at the neighbor environment here. Create SQS structures, and then finally the job management in pyiron, where you can reload jobs based on their job name. You can also reload them based on their job IDs, but we find job names are much more intuitive. Maybe we should also briefly mention how to get the job name, so we can always get the job name. With the job name function, we can look at the input of our jobs, execute the same job again, We can run the job again, but this requires the delete existing option set to true. And then we see here the final structure, the updated structure, this part, and then also publications. With this, I'd like to close the first session and then hand you over to the exercise. And once you finish the first exercise, we can continue with the next session. Thanks a lot.